In our introduction to jointly probability distribution or joint distribution for two variables, we can talk about the expected value for two variables that are jointly distributed. We're going to discuss two cases where x and y are discrete and also x and y are continuous. The expected value of a function h of x and y, which is denoted by e of h of x and y, or mu sub h of x and y, is given by, if x and y are both discrete, then you have the double summation of h times p. And if x and y are continuous, then you have the double integral of h times f dA. So for discrete random variables, we basically add all of those values together. And when it comes to continuous random variables, we have to calculate the integral. Now, we're going to define covariance between two random variables x and y. The covariance between two random variables x and y is the expected value of x minus mu of x times y minus mu of I, which is basically defined for discrete and also continuous random variables. When you have discrete random variables, it is the double summation. Well, this is a function like in previous slide, h of x and y. We're going to copy this guy down here and multiply it by p of x and y. And if you have continuous random variables, it is the double integral of the function h times f dA. Covariance are important in different cases. Like covariance is used to understand the relationship between different time series variables. This is useful in modeling and forecasting economic indicators. Also in the stock market. Covariance is used in algorithms for filtering and predicting the state of systems, such as Kalman filter. These algorithms rely on covariance matrices to quantify the uncertainty in measurements and predictions. So this is how we define the covariance between two random variables. If A and C are either both positive or both negative at the same time, then the correlation of AX plus B and CY plus D is the same as the correlation of X and Y. To define correlation, we are using the covariance. Covariance is basically the numerator. And for any two random variables, X and Y, rho is in between -1 and 1. The two variables are said to be uncorrelated when rho is equal to 0. In previous class, we talked about rho and R, correlation coefficient. So the covariance between two random variables x and y is defined this way. The covariance of x and y is the expected value of x minus the expected value of x times y minus the expected value of y, which we can write as the expected value. Now just distribute x into parentheses and then expected value of x into parentheses. So this is what are we doing? Basically then trying to simplify. Times y times expected value of x minus x times expected value of y plus the multiplication of expected values. Well, here you can write this as the expected value of x times y minus the expected value of y times the expected value of x minus the expected value of x times the expected value of y plus the expected value of x times the expected value of y. We're basically finding the expected value of these four terms, which is equal to the expected value of x times y minus the expected value of x times the expected value of y. You can basically cancel out these opposite terms. So that's how you end up with these two terms. Note that if x and y are independent from each other, then the covariance of x and y must be equal to 0. The definition of covariance and some properties of covariance. For any random variables like x, y, and z and constant c, first of all, the covariance of x and x is nothing but the variance of x. Remember that the covariance of x and x is the expected value of x minus the expected value of x times x minus the expected value of x, which in turn is the expected value of x minus expected value of x to the second power. But at the same time, remember how we define the variance. It is the expected value of x minus the expected value of x to the second power. So as you can see, the covariance of x and x is nothing but the variance of x. The second property, covariance of x and y is the same as the covariance of y and x. Well, we are going back to the definition. The covariance of x and y is the expected value of x minus expected value of x times y minus the expected value of y. And the covariance of y and x is the expected value of y minus expected value of y times x minus the expected value of x. Well, these are just commutative. They're the same. So you can easily see that the covariance of x and y is the same as the covariance of y and x. They are not different from each other. The next property, the covariance of c times x and y can be written as c times the covariance of x and y. So basically, if you multiply one of these variables by a constant like c, that constant goes in front of the covariance. Why is that? Remember the definition. Covariance of cx and y is the expected value of cx minus the expected value of cx times y minus the expected value of y. Remember that the expected value of c times x is c times the expected value of x. So basically, the covariance of cx and y can be written as the expected value of c times x minus the expected value of x times y minus the expected value of y. Or basically, you can take this c and write it in front of the expected value itself. So it means that the covariance of cx and y is c times the covariance of x and y. And finally, the covariance of x and y plus z is the covariance of x and y plus covariance of x and z. Well, we're going back to the definition. The covariance of x and y plus z is the expected value of x times y plus z minus the expected value of x times the expected value of y plus z. In turns, if you distribute x into parentheses and calculate the expected value, you get expected value of xy minus expected value of x times expected value of y plus expected value of x times z minus expected value of x times expected value of z. So basically, we defined the covariance of x and y and added to the covariance of x and z.